Oh, okay. Hey, welcome back here. We're getting ready to do our, looks like our fourth online lab here. And so we are into the fourth week and the fourth chapter. And if I were to describe this fourth chapter, I would say it's an applied chapter. We're going to take what we've been learning. And so this is really where things come together. This is where I think it becomes more interesting as an applied physicist myself. I like to see this in action. I like to see, okay, why do we care about all this? And so we've been doing electric fields and electric potentials and learning about the fundamental physics concept for the last three chapters. And then finally in this chapter we get into an applied one. And the next three chapters are all applying this information, making it useful. And so if you haven't got a chance to see the video lecture on this chapter 26 in the survey book, the one on capacitors, watch that first and work a little bit on that before you do the lab here, because there's a number of things you need to understand. And when you go and you see that one, or if you've already seen it, you will notice that the lecture is kind of long, and the lecture is really divided into two parts. The first half of the lecture is really, what is a capacitor? What does it do? And you'll hear me say that it does many different things. And one of them is just to store charge. And so that's kind of the easiest way to kind of give one of many reasons of why we care and how they are useful, these capacitors. Okay. The other half of the chapter is talking about, okay, what if you have more than one capacitor? Now that we already understand what a capacitor is, what if we have two or three of them hooked together? What are the advantages of disadvantage of this hooking them together in series or in parallel? And so I want you to catch all that, because that's exactly what we're going to do here. So assuming you've already looked at that, I'm going to open up the lab manual, and on page 16, and let me encourage you to go page 16 in the lab manual. The author talks a little bit about what capacitors are. It talks a little bit about the capacitance meter that we have. In fact, I'll hold it up here, but I'm going to encourage you to kind of look at your lab manual, because the lab manual has a picture, if you will, of this, the front part of this we're going to be using to measure capacitance here today. And the procedures start here on 17, and I would define this lab as broken into those same two pieces. Steps 1 through 4 are going to be asking us to hook up different capacitors and see what happens when we have more than one, and what happens when we hook them in series versus parallel, or some kind of combination between them, and give us a little bit of exposure and a little bit of experience doing that. Whereas then the second half of this chapter, lab, which, like the second half of the chapter, or actually it would be the first half of the chapter, is talking about, well, what really is a capacitor? Let's build one. Let's investigate it by changing the parameters that we built. And that's what we will do here. We will use these two metal plates as the two metal plates on our capacitor. And so we'll actually build it and do a couple little experiments with it. All right, so let's do the first half, and we'll kind of break that into two halves. In fact, it's going to take a lot of whiteboard work today, so I'll probably do the first half and then erase all that and come back and do the second half. All right, so grabbing a marker and maybe moving to that far end, but reading this first question, the first question says this. It says, use the capacitance meter. All right, well, let me pause right there, because if this was an in-face one, I would ask you guys to pick up your capacitance meter, which sadly you can't do here. So I hope this comes across on a video enough that when we return to the classroom or you transfer on, you'll have a good enough feel that when you pick up a meter, whether it be this meter, which is a capacitance meter, and I'll kind of jump ahead, we're not there now, but starting into the next lab and through the rest of the semester, we'll also use this handheld meter. And so both of these we refer to as digital multimeters, DMMs. This digital multimeter measures voltage, resistance, and current. This one here measures capacitance, inductance, and resistance. And diodes. So I just want to show you today, even though it does many things, is kind of how to use the dial settings, but it's kind of universal for all of our handheld meters. And so I'm going to hold this one up, and of course probably the biggest thing is to find the on switch. This on switch is a little confusing. It just says off, it never really says on. But if you move it from the off to the first little setting, there's a D. That D actually stands for diodes, and so if you wanted to measure diodes, that's where you would put it. That's not what we're interested in. I'll go to the next one, which is called the LCR. That's why we often refer to this as an LCR meter. Again, you'll see that on page 16. Hopefully you can also see it a little bit here on the video. But the L, the C, and the R, as we'll learn throughout the semester, the L is for an inductor. And this part down here, this bottom 1/3 of the dial, has an L, and that would be where you would set it if you were trying to measure an inductor. And we will, just that'll be many weeks away. The C part of it is what we want. The C is for the capacitor. And so that's on this third of the dial. So I'll turn it over here. And if you're looking at your little picture on page 17, you'll see the little dial broken into the 3 pieces, and it's pointing towards a piece over here on the capacitor. And I'll just touch on it, even though we don't need it today. Over here is the R. That's if you wanted to measure resistance. And so more on that in the future. This first application chapter is about the C part of this, capacitance. Then we'll go to resistors, and then we'll go to inductors as the semester moves along. Now, hooking them up is pretty easy to the meter. You just take a wire with these banana jacks and you just plop them in. And for this meter, there's only 2 connections, so it's really easy to say, well, where does it connect to the meter? Now, I point that out because next week, when we do this digital multimeter, there's 4 connections. And we'll need 2 of those 4. And which 2 of those 4 can be a little confusing depending on what our settings are. So that one's going to take a little more thought, and we'll talk about that one when we get there. But for us, it's just simply, hey, just connect up the plus and minus. And then this just goes right to the 2 ends of your capacitor. And so what I have here today is 3 capacitors on this little board, and 1, 2, 3, 4, 5 on this little board. Now, we're not going to be using all 8 of them. As you'll see here in a moment, we're asked to use the, well, this is kind of loose, let me tighten it up, but we're not using that one. We're asked to use these 2, top yellow ones, and this top orange one. And those are the 3 we'll be messing with in steps 1 through 4. But it would simply just look something like this. You would take the meter and you would connect it to the 2 connections. And that's it. And there it is. And then you take your reading. Now, there's one more thing I should say about the meter as we get started. The part I already said is the dial needs to be over here at the C's for the capacitors. But there's also some other numbers here, and those numbers say what is the maximum that can read. Like right now, I am at the smallest setting, and it says 200 picofarads. Now, what that means is this can read up to 200 picofarads. If your capacitor is more than that, you can't read it on this setting, and you'll get kind of a weird number here. Same thing here. This is 2 nanofarads. And the 2 nanofarads, this is the machine saying, look, I can read up to 2 nanofarads, but if yours is more than that, which this is about a 1 microfarad I'm hooked to, then I can't read it. And then the meter's kind of telling you that. It does this little 1 at the end. It's kind of it's saying it's overloaded. All right. So what that means is if I scan down here, the best one I should be at is this one here that says 2 microfarads. Because again, that would mean it could read up to 2 microfarads. And since I'm trying to read something at about 1 microfarad, that'd be a good setting, because the one lower than that is 200 nanofarads. All right, so that would be too low. Now, technically, you might say, well, the higher ones could read it. Sure, but you lose the accuracy of your decimal point. And so you don't want that. So you want it as low as you could go without overload. And so that's kind of the usefulness of these handheld meters and why they have lots of different settings. And that's where we're going to get started here. If I read step 1 here in the lab, it says find these 3 capacitors. It says a 1 microfarad, and so as I already pointed out, there's the 1 microfarad. It also says find the 1/2 of microfarad. That's going to be this one here. And it says also find, and there's a little typo on page 17, it should say find the 0.47 microfarad capacitor. There it is. And as we do the rest of the lab, you'll see it keeps referring to this one. So that's why I know there's a typo there in step 1. Okay, so what we want to do is to then measure the accuracy of this one that says it's 1 microfarad. But this will also illustrate something that you need to learn about electronics as we go forward, is these things are mass produced. Remember, a capacitor is just these metal plates, and they just mass produce them. And if they do it real quickly with very little care, they won't get exactly 1 microfarad. They'll get something close to 1 microfarad. So in a way to keep costs down, but a sacrifice of accuracy, they just run these off of a mass-produced machine really quickly. That keeps our electronics low, and then fortunately, our cost of our electronics low, and then fortunately, it doesn't have to be that accurate. And so that's what we have. So we've got this mass-produced capacitor, which says it's 1 microfarad. But what that really means is within about 10%, it's 1 microfarad. And so they took some care to make sure that it was accurate within 10%, but not much care. And that's why we need to find out what its exact value is before we move forward in the lab. But it also gives us a chance to figure out then what that really means. All right, so I'm going to grab my 2 capacitor boards and walk over here to the whiteboard and say, okay, here is step number 1. So number 1 is really saying find what I'll call the true value of your 1 microfarad. We know it's close to 1 microfarad. So I'm going to put here 1 microfarad, but, and this might look funny. Well, why don't I just do an approximation? Because it is approximately 1 microfarad. But using my meter, as you probably already saw, I'm looking at a number as 0.981. So 0.981 microfarads is a little bit more accurate. And I say a little bit more accurate because my meter even has a 2% error in it. So this would actually be plus or minus 2%. So again, you never really know what the true value of something is. There's always some kind of error, but just because it came off the manufacturer, I know it's within 10% of the 1 microfarad. And now that I've measured it, I know it's within 2%, because that's the accuracy of my meter, of this number. All right. Let's try that with our other capacitors. Let me switch here for you, and maybe it'd be good for you to watch, but I'm just going to, again, disconnect. And here's my meter, so I know it's kind of low there. You can kind of see it, and I'm just going to plug it in again. And then I'll hold it up. And now remember, the manufacturer says this is about 1/2 microfarad. And I will then put 0.5 microfarad. But that's really plus or minus 10%. So it could be a little over, it could be a little bit under. In fact, most of them are pretty close, right? If you've done your Gaussian curve distribution in your statistics class, and maybe that's a little further than your education is right now, you know that there's this standard deviation. So when they plus or minus 10%, only very few of them are as far off with 10%. So this one is pretty close. It's like this one's within 4%. I get a 0.484 microfarads. Okay. And then the third one they ask us to do, and I'll hold that one up too, And so here it is. And they say this is supposed to be close to a 0.47 microfarads. And so we should be within 10% of that. But I can measure it more accurately, and so I am going to. So using my meter, I've got 0.45, and it's going back and forth. I'll call it an 8 microfarads. And so there's step one. Step one just says practice using your meter. Find the accuracy of these three that we're going to be using. So like I said, a very practical lab, and one that would be really a lot better if you were in here. But on the other hand, if you were in here, you might get sick with coronavirus, and that wouldn't be good either. So that's why we're doing the way we're doing this semester. All right, so that's the idea here. Let me continue on and see what they say, because they have some calculations for us to do, and I will probably leave most of the calculations for you to do and the graphs for you to do. So again, always think of me in these online video labs that, I'm your partner, but as far as I'm partner, I'm collecting the data, but for you to participate a little bit more, you'll do these calculations, because look at this. It says write and record the values and the percent difference, okay, from their measured value. So in other words, this one is off a little bit. Now let me at least do the first calculation with you, but it's saying how much is it off? What is its percent error? Let me come back and read. Did it say error or difference? That might be important here. Measure the values and the percent difference. So they want to know the difference between these ones. So a percent difference is defined this way. Of course, as the name kind of implies, if you have two measurements, A and B, you take the difference between them. Okay, so in a moment, I'm going to take the difference between these two. So how far do they differ? In other words, what do they say it's roughly equal to, but what is it really equal to? Or, like I said, really within 2%. And then divide, and here's the important part between a percent difference and a percent error. Because a percent error, we would divide it by the known value. We're going to call this a percent difference, meaning how close are these two numbers? In other words, we're not going to really say which one is the correct one. But I guess I would probably say this is probably the more correct one. And so I might say how much is this error, how much is this one off of the real value. But when you do a percent difference, then they're talking about dividing it by the average of those two. And so how far do these two basically differ by? And as I said, the manufacturer, when they make them, says that will be no more than 10%. We can guarantee you that. And so let's see what ours did. And ours are usually pretty good, because I'll tell you what I've done in the past. We just buy a big box of them, and when we measure them, and anything that is, far off, like even 5% or more, we get rid of them. And so all of ours are really close to their numbers, and that's how you'll see that throughout the semester. So most of ours are pretty close to the stamped value on them, because we just kind of, the ones that aren't, we just have already recycled them. So they're not even around anymore. Although we're getting, if we've ever got to buy a new box, I guess we'll have to go through that again. Now to make it a percentage, we would say times 100 for a percentage. So in this case, I would have something like a 1 minus a 0.981 all over 1 plus 0.981 divided by 2 multiplied by 100. All right, so if I grab my calculator, the 1 minus 0.981 is going to be in the numerator. That's 0.019. And down here in the denominator would be the 1.982 divided by 2, which is 0.991. And if it'll be okay with you, I won't actually write this out. This is the kind of stuff I'm going to let you continue to do the calculation on. And so if I go the 0.019 in the numerator and divide it by 0.991 and multiply that by 100, I'm at about 1.9%. And of course, doesn't really surprise you. Since this is a 1, that's obviously 2% below, or a little less than 2% below. So I kind of expected that. That wasn't a big surprise in my calculation. But here's what I'm going to ask of you then. And so go ahead now and calculate the percent difference of the rest of these and keep them close at hand. All right. As far as my whiteboard work goes, I'm going to go ahead and, well, maybe I'll leave that there in case you wanted to come back there. All right, I'll leave that first calculation, but you need to go ahead and calculate those other 2, and so I'll move on to step number 2. And I was going to erase it so I can move step 2 up there, but I think that'll work fine. All right, so let's come over to number 2 here. Number 2 says this. It says, connect the 1 and the 1/2 of microfarad capacitors in series. Let me pause right there. This is the important part I wanted to make sure you've already done the lecture on, because I explained what is a series and what is a parallel connection. And to quickly repeat that, series means they go from one to another. For example, you did 121, then you went into 122, although maybe that's not a good example because he could have gone into 123. But you got to do 121 first. Maybe your math sequence is a little bit better because you got to do calculus 150 and then calculus 160 and then math 200, and then it gets some parallel stuff. So, but the point is it's sequential. Your education, you had to go through middle school and then to high school and now to community college and then eventually a 4-year school and maybe even onto a graduate program. But they're sequential. They're one after another. That's what series means. So that's why we like to write it this way. And so the symbol for the capacitor, as I hope you got out of the lecture, is something that looks like that. And literally because, and I'll come back to show you today's equipment as well as in the lecture, this is physically how a capacitor is made. It is one metal plate and another metal plate, and of course a wire connected from it. Now this one doesn't have a wire connected from it, but in a little bit when we use it, I will connect a wire right here. And I have the same thing on this one too, but I'll get to those in the second half. I just wanted you to understand then why we use that symbol. It's a great symbol because it's got the metal plates, that's the capacitor, and it's got the wires hanging off here. So let me call this capacitor number 1, and this is the one that they say would be the 1 microfarad. Now, please remember for the rest of the lab, when they say the 1 microfarad, they mean the one that has written on it as 1 microfarad. It's not really a 1 microfarad capacitor. As you can see, it's a 0.98. 1 or 2? How come I did a 1 here, or 2 here? Yeah, I'm not sure why I did that. But forgive me, maybe I was thinking ahead, and probably what's happened is I was thinking faster than I was writing. But that's such a small one, it's not going to change this, so I'm going to leave that alone there. Okay, so that's the 1 microfarad. And then it says hook in series with it now I've talked so much I forgot which one it said. I believe it was a half. Yeah, the half a microfarad. So let me put C2 for capacitor number 2. And again, let me remind you, this is not exactly a half a microfarad. That's why we measured it here back in step 1. This is a 0.484 microfarads. And when they say hook it in series, here's what they mean by that. They say connect from this one right to that one. And so I'm just going to put a solid connected right there. And so that's how we will indicate in a drawing that we are hooking the two together. And in this case, it is in series. Basically what that would mean is if I were to hook this up to a power supply of some type, and this side would, let's say, be hooked to, say, the negative of the power supply, a bunch of negatives would accumulate on this plate. Now, negatives repel other negatives, so they would chase off negatives on this plate, and those negatives would have to go across that wire to the second capacitor. I would call this the first plate of the second capacitor. And so now you can see this word series. This is what we mean by series. It goes from this one over to that one. And of course they would chase them off. And so one of the things you saw in the lecture, and I'll repeat it now, is that capacitors in series like this end up having the same charge on them. They have to. That's that principle of conservation of charge that we saw back in chapter 23, that they would go from here and push them onto here. Now, for today's lab, we don't need to really worry about they having the same charge, although it's nice to repeat it so that as you're working on this, you'll always remember capacitors in series have the same charges that build up on them. We're not going to actually hook it to a power supply and build it up. We're just going to do this. We're going to say, if you were to hook two capacitors like this, those two would be the equivalent of one. And that's why I wanted to make sure you went through the lecture, because I kind of proved this, that you could think of those two as one. And what is that equivalent capacitance? And what we learned in the lecture, let me write it here, is that the equivalence capacitor is related to the capacitance of the other two. And so this is that nice little formula. What would this be equivalent to? And so what you're asked here in number 2, and let me keep reading here, it says actually measure the equivalent capacitors and then compare this to theory. All right, so here's the part I'll let you do. You need to get out your calculator and you need to put in these numbers. And you need to calculate this equivalence capacitance. And I'll just put a calculate here. And calculate what that equivalence is. Because then we want to then measure this equivalence. And of course, if our theory is right, what we calculate and what we measure should agree. And this lab is designed, of course it's not designed to be remotely done, so I hope it's going to come across here somewhat reasonable. But this is really a good chance for the students to test their calculation and test their measurements. And if those two don't agree, then you're doing something wrong. It could be with the calculation, it could be with setting it up and making the measurements. Now, this is the part being remotely you can't do. You can't actually hook it up. So I hope I don't make the mistake. I hope the mistake's not on my end. If these two don't match, hopefully the mistake is on your end and you can recalculate here. So I'm going to actually hook it up and measure. All right, so I'm going to come over here to my capacitors. And remember, we're talking about the 1 microfarad. That's this top yellow one. And we're talking about the 1/2. That's this top orange one. And if I just take a wire over here, I've got a bunch of wires just sitting down here for this reason. Let me take and kind of hold this up, but I would say this connection right here would be this in the picture. This would be what I'd call the first plate of the first capacitor. And then this other side is the second plate of the first capacitor. And then this is the wire that I'm going to use to connect to the first plates of the second capacitor. And so hopefully what we draw on the board looks a little bit like what I hold here in my hand. And so there is my two capacitors in series. And so to think of this as one, what I'm going to do is just kind of hold this together in one hand and say, okay, think of this as one capacitor. And what is the capacitor from here, the first plate of the first capacitor, to over here, which I'll call the second plate of the second capacitor. So here's where I will then take my voltmeter, which I sadly just pulled the wire out. And if I can lift it up without breaking the meter, I can see the meter there. I will hook up the meter to one side and then the other. And then I will hold it up for you to see, and my measured value looks like a 0.325. And so 0.325 microfarads. Okay? Now, like I said, I want you to do this calculation. However, I also want to help you a little bit with your calculator, because let me show you an efficient way if you're not already familiar with this. Why don't we think of this equation as the following? The inverse of the equivalence is the inverse of capacitance number 1 added to the inverse of capacitance number 2. Now, the reason I like that is because these calculators, and I happen to be doing the TI-84 Plus, but whether you have the 83, the 84, the 85, the 86, the 89, or the other brands, they have this nice reciprocal key on here. And on mine, it's just right there, and it means I can do this. I can take this first number, which is 0.981, and just hit the reciprocal key. And then hit the plus. And then the other one is the 0.484, and hit the reciprocal key. So I'm just adding reciprocals. I'm taking advantage of that reciprocal key. So when I hit enter, that is the sum of the reciprocals. Now I'm not quite done, because to get the answer, I need to take the reciprocal, which is great. I just hit that reciprocal key again and hit enter, and I get 0.324 microfarads. Oops, I said I wasn't going to write it down, and I did. But I wanted to show you that calculation. I wanted to show you the reciprocal key of that. And so my comment usually is in class setting is if those two agree with each other, you're good that you are understanding both how to do the calculation and how to actually hook it up and make the measurement, and then so move on to the harder ones. All right, so since those matched, let's move on to the next one. And so number 3 is a little different. It's not too much different before we get to the hardest one, and not real hard compared to the homework ones. But let's look at step number 3. Number 3 says connect the 1 and the half, and that's what we did before, but this time in parallel. All right, so parallel. What does parallel mean? Well, without talking too much about it, hopefully this is what you got out of the lecture, but parallel means you can have both at the same time. Maybe driving on a freeway, you will notice that there are different lanes. Those are all parallel lanes. They are all going in the same direction. And a given car, let's say your car, doesn't go in all the lanes. You pick one and you go that direction. Other cars go in the other lane. And so say between here and Carp, there's a bunch of cars going to CARP. Some are going in the fast lane and some are going in the slow lane. Well, some of the parts of the freeway have 3 lanes, but other parts have 2 lanes. I'll just say on where the parts where it's 2 lanes, I would have those 2 options. And so that's what we mean by parallel. Parallel would mean something like this. If you took your first capacitor, so let's call that capacitor number 1, you would want to hook it up so that these 2, and I'll just connect them something like this, and say, see, this is a parallel connection. You see, I know it's a parallel connection because if I were to hook this to a power supply and electrons were to come in here, some of the electrons could go over and accumulate on this capacitor, but some of them would go this way. They have 2 options. And just like the cars, there's many cars, but for a given car, for a given electron, one electron only goes one way. It doesn't go both ways. It's not the series. It doesn't go one into the other, and that one electron goes through both. That's what we just did in step 2. That's a series connection. But a parallel connection is where they can go an option of either way. I guess it would be like saying our classes here are in parallel with the classes down in Ventura or are up in Allen Hancock. You could go to this community college and take our series, or you could go to Ventura and take their series. Or you can go to Hancock and take their series. But you wouldn't do both. You wouldn't go through our physics series and then go down to Ventura and take their physics series. That makes no sense. It's either one or the other before you move on and transfer to the 4-year university. And so that's a different connection. And the behavior of our electronics is very different. And so we like to separate these so we understand, hey, this is series, this is parallel. By the way, I should point out, there's series, parallel, and also there's neither. Sometimes we spend so much time talking about series and parallel, we think everything has to be either series or parallel, but we can also, for a complicated circuit, have a connection that is neither of those. And we'll see some of those in a couple of chapters. So, but right now, let's just learn the basics, and that's series versus parallel. Okay, and so if I were to connect this together, and then that means the electrons that were chased off of this